Submarines running on diesel-electric engines share a fatal flaw with traditional space probes. They are completely dependent on their environment. A diesel sub has to surface for oxygen to burn its fuel, exposing it to radar, while a space probe relying on solar panels will eventually freeze when it ventures out of the sun's reach. This environmental dependency extends to modern medicine. When we treat cancer with bulk chemical therapies, we operate with broad strokes, often destroying healthy tissue right alongside the tumor because the treatment lacks cellular precision. Human innovation is hitting a hard ceiling. We are trapped by the physics of the macro world, forced to play by classical rules, where materials are manipulated in chunks of trillions of atoms at a time. Pushing past this threshold requires a shift from sensory perception to mathematical modeling. By calculating and manipulating matter we cannot see, we can effectively bypass the classical rules that govern the bulk world. Overcoming our earthly limitations requires us to master two completely distinct invisible domains: the physical architecture of the molecule and the raw thermal energy of the nucleus. Let's zoom down to the nanoscale, a space measuring between 1 and 100 nanometers, where you are dealing with mere hundreds or thousands of atoms. Down here, the physical rules that govern bulk matter simply stop working. This diagram illustrates the mathematics of surface area. If you take a single, solid block of material and calculate its surface area, then chop that exact same volume into 1,000 much smaller cubes, the mathematical ratio of its surface area to its volume explodes, exposing 10 times more material to its immediate surroundings. Because so much more of the material is exposed, it becomes incredibly reactive. Bulk gold sitting in a vault is famously inert, but if you break it down into highly reactive nanogold, it becomes so potent it is currently engineered to hunt and destroy cancerous tumors. This physical shift is driven by quantum effects. When you restrict electron movement within a tiny atomic lattice, a material's physical behavior becomes dictated entirely by its specific size, rather than what chemicals it happens to be made of. Quantum dots in modern displays are a perfect example of this. A dot that is 2 nanometers wide will emit a completely different color of light than a 5 nanometer dot made of the exact same element. We can also use physical size to engineer extreme structural repulsion. By replicating the micro-nano dual structure found on a lotus leaf, manufacturers create hydrophobic surfaces that force water to bead up and roll away, taking dirt with it. At the nanoscale, we are no longer trapped by the traits a material exhibits in nature. By engineering its physical dimensions, we can program matter to behave exactly how we want. Now we zoom even deeper into the architecture of matter, down to 10 to the negative 15 meters, right into the nucleus of the atom. Here, the focus shifts from structural design to high-density energy generation. Nuclear transmutation and alpha decay function as continuous thermal engines. As an unstable nucleus sheds an alpha particle to find stability, it releases a steady, predictable stream of heat. This black cylindrical unit is a radioisotope thermal electric generator, or RTG. Inside its secure chamber, the natural alpha decay of plutonium-238 creates intense thermal energy, which specialized materials convert directly into continuous electrical power without a single moving part. Thanks to a fuel source with a half-life of roughly 80 years, RTGs have allowed probes like Voyager 1 and 2 to operate for decades, continuing to transmit data from beyond our solar system in total darkness. While RTGs provide electrical power, nuclear fission provides immense thrust and heat. Because splitting an atom is a completely anaerobic process requiring zero oxygen, a nuclear-powered submarine can remain submerged and hidden for months, limited only by the food supplies for its crew. By mastering these specific nuclear processes, we decouple our most critical defense and exploration technologies from the environmental constraints of Earth's atmosphere and the sun's light. Scaling back to the human scale, we see the shift toward intentional material design. By manipulating the building blocks of matter directly, we can construct the exact physical properties required for a specific task. Using tools like the scanning tunneling microscope, scientists bypass the visual limits of light entirely. This technology allows researchers to observe atoms as they vibrate and physically pick them up, placing them one by one into custom structural lattices. This level of precision fulfills a prediction made in 1959 by physicist Richard Feynman, who envisioned a day when humanity would possess the tools to arrange matter atom by atom. Today, that vision is an industrial reality. Nuclear science, driven by innovations like small modular reactors and thermal propulsion, secures our energy independence, while nanotechnology provides a near-infinite capability to engineer materials with properties not found in nature. When a nation can generate power independently of global supply chains and engineer materials that solve specific biological or mechanical failures, it gains a definitive level of technological sovereignty. Mastering these invisible extremes is what ultimately dictates long-term persistence on Earth and across the solar system.